Suppose I have an inductor and I define a voltage that is across that inductor, and I define a current that's flowing through it. And by the way, the current should be in the passive sign convention, should follow the passive sign convention. It goes from positive to negative. Conventional current flows from positive to negative. Then I have that the voltage on the inductor is L times di dt, right, that we previously learned about. But what if I want to solve for current? So we sort of rearrange this equation to solve for current. Well, one of the things that I can do is I can integrate both sides with respect to time. So I can integrate my voltage. I'm just going to write V here for voltage. So I can integrate voltage with respect to time. And L is a constant, so when I integrate it will come outside, and I can integrate the right-hand side with respect to time. And I would usually do this integration over some limits, so let's say from 0 to some time t here. Now, just to clarify this notation, the upper limit of my integration here is not the same thing as the variable of integration, and I'm being perhaps a little bit sloppy in the notation to use the same letter for both of those. You will see sometimes that some people will write this instead as something like integral like 0 to tau v. It's like integral 0 to t of like v of tau d tau, and use a different letter for those. So you can do that if you prefer. That's a little bit more kind of mathematically precise, but I'm going to just sort of use the perhaps slightly less precise form here and use the same letter for both, but you should remember these are not the same variable. So the right-hand side here, you see I have the integral of a derivative, so I can, of course, simplify that. And what I will end up with is that there will be I of t minus an I of 0. So those are my limits of integration. And then I can rearrange this here for my current. So my current in the inductor is 1 over the inductance times my integral of my voltage. So I'll write V of t. To be super clear, this is a time-dependent function. The voltage is a time-dependent function, plus the initial condition, the I of t, is like a constant of integration. It will be what is the initial current in the inductor. And so it is important, we always need to specify what that initial current actually is. So this here is another very important equation, and if you're not comfortable with deriving it, what I just did then, this is another equation that you should learn. On the other hand, you could just start with the definition of the voltage and then just very quickly integrate it to get down to this expression here. So let's have a look at using this in a problem-solving example. So this one, example 6.2 from the book, and we have a 100 millihenry inductor, and there is a voltage, which is a time-varying voltage. So this is a voltage here, time-varying voltage, and we are asked to calculate what is the current that is flowing in this inductor, given that we have an initial condition of 0. So the approach for this is we use the equation that we just derived above. So that is this 1 over L times the integral of our voltage with respect to time plus our initial condition of current. And our initial condition is just equal to 0, so we can immediately cancel off that term. And so what this reduces to is calculating an integral of this expression. So our expression will be for positive times, which is the region that we're integrating over. It will be 20 times t times e to the minus 10t dt. Now, to do this integral, we need to actually integrate by parts. So you notice we have here a product of two terms, so we need to integrate this one by parts. So in order to do that, I'm just going to calculate that integral separately, just to make this super clear. So need to integrate by parts, in case you're a little rusty with this sort of mathematics. So what I'm trying to calculate is an integral from 0 to t, and I'll just leave out the constant of 20. I can bring that outside my integration. So I want to know integral of t e to the minus 10t dt. And in here I will do my integration by parts. So I will let variable u equal to the first factor, so that's the polynomial term, which means that I have du is equal to dt. That's nice. And therefore the other part, the dv part, will be e to the minus 10t dt. And so I can integrate that one. This will give me v is minus 1 over 10 e to the minus 10t. And so therefore my integral was 0t t e to the minus 10t dt is going to be u times v taken over our limits of integration minus the integral of v du. So let's substitute in our values. So u substitute gives me t, v gives me minus 1 over 10 times e to the minus 10t, and that is taken over these limits of integration, minus integral 0t, so v 1 over 10 e to the minus 10t du is just dt. Then the first term on the left-hand side, when I substitute in my limits, replace t with t, nothing changes. When I replace t with 0, it will vanish. The term, the whole thing will go to 0. So substituting in those limits, all I end up with is negative t e to the minus 10t, all of that over 10. And then my integral, I'm going to kind of bring out the positive, cancel the negative sign so it becomes positive, and then the value of my antiderivative dividing through by the negative 10, so I'm going to get another factor, another negative sign, and another divide 10, so that will give me total divide 100, e to the negative 10t, and that's also over the same limits of integration. So we have the following. Substituting, so I'll just bring my minus 1 on 100 out the front, and then I have my limits of integration, which will be e to the minus 10t, and then a minus e to the 0. E to the 0 is 1. So we're almost there. It's going to be minus t e to the minus 10t over 10 minus e to the minus 10t over 100 plus 1 on 100. And so that's the value of my integral. So let's go back and look at where we were headed with this. So the thing that I'm trying to evaluate was actually this integral here. So let's just write that one a bit further down so we can kind of see what we're doing. So it was I of t is bear with me, is 1 over L e, 1 over L integral 1 over L integral 0t of 20 times that thing that I was just integrating, 20 times t e to the minus 10t dt. And so based on what we've just calculated, bringing the 20 to the front of my integration and subbing in value for L, so let's just clarify what we're doing here. Substitute L is 100 millihenries, so converting to base units is 0.1 henries. So that gives me 20 divided by 0.1. multiplied by this integral that I've just calculated, so that's a minus t e to the minus 10t over 10 minus e to the minus 10t over 100 plus 1 on 100. And we can simplify a little bit here, so the term at the front is going to give me 200. I'm going to put the positive term first, so that's a 1 on 100 minus, let's just take this term, this middle term, and then finally minus t e to the minus 10t over 10. Bringing that 200 through will give me 2 minus 2 times e to the 10t minus 20 times t e to the minus 10t. And that will have units of amps because that is a current. So to recap our problem-solving strategy, when we have the voltage across an inductor, we can also calculate the current, and the way that we do that is with this integral expression here. So substituting in our value for the voltage, we then have to just evaluate the integral. It becomes a math problem. We evaluate the integral and we're able to solve for the current. So you see we can kind of go in both directions. So coming right back up to our fundamental definition, this is the relationship between voltage and current. And if you know voltage, you can calculate current. And if you know current, you can calculate voltage. And it works in both directions just by taking derivatives or integrals, depending on which one you're trying to solve for. But if you're calculating the current through an inductor, then it is this formula here is the one that you need to use.